seats. Yeah, the afternoon session will start. Okay, good afternoon, everyone. I'm Yuan-Tseh Wang from ASIAA. I'm the session chair of the last session. Before the technical presentation, we have the honored speaker, our former president, the Yuan Li, and supposedly he should give the talk yesterday, the first talk, because if you remember, you want to push the project. One of the key points is you need a godfather. Really is our godfather. Okay, so let's welcome our godfather to say something about the talk.
Distinguished guests, for all, ladies and gentlemen, when I came back from Japan last night in the airplane, my wife asked me, what are you going to do tomorrow? I said, I'm coming to Institute of Astronomy, Astrophysics. My wife was so disappointed. She said, Yuan, that was last week. So I said that's going to take place this week also. Because only for home. So I didn't have time explaining to my wife I'm doing the right thing. So I'm sure I'm in the Institute of Astronomy and Astrophysics. Well, I remember about 550 years ago, when he was 12 years old, he wrote a poem and said, 山近月圆觉月小, the mountain is close, moon is far away, so you feel the mountain is big. So he said, mountain is bigger than the moon. But he said, if you have a man with an eye as big as the sky, then you see the high mountain where moon is even wider. And that was a poem written by a 12-year-old kid. And when I saw Paul Hall, you see, 30 years ago, started when I said birthday, and looked through all his academic career, and I felt he was trying to make his eye as big as the sky, and get bigger and bigger. Now the eye is as big as an earth, but not as big as sky yet. But he was quite nice. He always comes to my office and tell me what's going on in astronomy and astrophysics. And one day he said, with the new telescope, you can see telescope, observe the telescope on the surface of the moon. I was very impressed. One day maybe somebody playing tennis game on the moon, and this telescope was doing a tennis match on the moon. When we were Astronomy Institute, Astronomy Astrophysics, we started out at the high level and setting up the collaboration with our Smithsonian on the way. It's moving pretty well. And as a former president, setting up several new institutes, I knew we have to find good leaders and good vision and lots of money. the land and build the building. So all those years, I enjoyed developing the Institute of Astronomy and Astrophysics, and I did follow up to the stage to building up this millimeter array telescope in Hawaii, Maunakea, Maunakea. And at that time, I really see telescopes bigger, see smaller, and then become an array of telescopes. And ARMA, I didn't get to see it, and I observed and moving on and on, and I enjoy what's going on immensely. I see this picture of black hole. He was very excited coming always with the picture of black hole. And so, although I have not been able to help much of the entire from the presidency of Academia Sinica, it's been keeping me up. And I know you will have a telescope as big as the sky. Not yet. You have the telescope as big as an Earth. I mean, the telescope in Greenland, in Chile, Taiwan, in other places. Now the telescope as big as an Earth. But I know pretty soon you have observer on the moon, and gradually you have an eye as big as the sky, and you can see everything and how we started and how we are going. But thank you very much for this opportunity to come back. I'll go back to tell my wife I didn't make a mistake. Astronomy Astrophysics second time during the week. But thank you very much for seeing you.
Paul, you want to say something to your godfather?
Yes. The start of the institute, just as Yuan-Tseh said, we went to Berkeley to meet Yuan-Tseh at the time in his office. There were about 8 or 7 of us going there. Why? Because at that point he was not yet Yuan-Tseh, but we all expected that he was going to take over the academy, and we thought we should let him know what we were thinking. So we actually informed about our plans and wishes to join the submillimeter array project with Smithsonian, which was to come later on. And I remember at the time we talked about that as to whether that's a good project or not. And I don't know whether you remember. He said, "Oh, they have 6 elements. Taiwan can add 6 elements if Frank Shu returns." But only Fred Lowe returned, so it was only worth 2. But it was nevertheless a great start for us, right? And the other thing was very important, in the early days. We explained that doing science was very important, and we didn't care where we stayed and where our offices would be, but the most important thing was to have a project. And Yuan-Tseh agreed, and that's how we started with this submillimeter array project. And of course, years later, I constantly asked him for more budget, and he always helped me and helped us all along the way for so many years. We are not here if not for Yuan-Tseh leadership all of these years. So as you can see, he continues to come and help us and support us, coming twice a week. When he has a chance, he has a chance, he always helps us, and I see him every time I'm in Taipei, just about. If I can find him, I'm always reporting. So thanks very much.
Yeah, thank you very much, Yuan-Tseh.
Thank you.
come back the regular program. Each talk had 15 minutes. The first talk is given by Suijian about the two spectroscopy telescope initiative.
Yes, we can see your screen. So when you are ready, please start your presentation.
We cannot hear you.
他听不到吗？
No, we cannot hear Suijian.
Please unmute. Can you speak? 这边不能 mute。哎呀，不对，这边 mute， 这边 mute， 这边不要 mute， 这边不要 mute。
Just a moment, Suijian.
Can you try? Can you try?
Can you say something?
Audio.
No audio.
No audio.
Yeah, no audio.
好，let's switch to here. Mute, and we switch here.
So maybe we need some kind of AI system. They can switch automatically.
Suijian, can you hear us? Okay, good.
Okay, good.
可以听到吗？
可以。
可以听到吧
Yes.
？Okay, good.
Yeah. So you can start your presentation when you are ready.
Can I start?
Yes, please.
Yeah, thank you for this another opportunity. I find the subject of my talk is exactly in line with wisdom theme we heard yesterday. Our guiding principle is the future in the next generation. So in talk spirit, I can make a bold talk here. The next generation twin telescope initiative. I believe most of you are aware the famous high-level survey projects I listed here. However, it's worth noting that some of the Chinese projects have limited exposure in comparison. Among these projects, there are these initiatives. One is the commissioning phase on front. All these projects aim to explore both the evolving universe and its dynamics in two-dimensional space, so as to achieve the cutting-edge scientific goals. These goals comprise various fields, including the cosmology structure, galaxy evolution, galactic archaeology, as well as the study of children. So there's a growing demand for an additional dimensional information, as well as the internal physics and chemistry data that can only be provided through massive scale spectroscopy. Unfortunately, such a facility this for architect. This creates a so-called bottleneck in astrophysics. Let's take three space station telescope, CSST from distance. It's a 2-meter telescope for multi-color surveys with planet, wide and deep sky coverage. Its limiting magnitude will reach down to 27 to 25 in different colors. Now imagine how, without a large, massive spectroscopic facility, one can effectively conduct extragalactic studies spanning from the local universe
to the deep cosmos. Thus, CSST on its own critically requires such a facility to create signatures with deep imaging. Actually, there's a worldwide accepted consensus that massively multiplex spectroscopy is required to fully realize the primary science goals of those significant going surveys. You can find actually similar recommendations in the decadal surveys in the US, Europe, Canada, and Australia. Now, actually, CFT MSE, the MSE project the MSE stands for Maunakea Spectroscopic Explorer, is among the ongoing international collaborative projects in this nature. After years of trade-off study, it has evolved into a conceptual design, featuring 0.5 meter segmented pole mirror configuration. The design boasts a very large field of view, 1.5 degree field of view, and capable of accommodating nearly 20,000 spectral fiber. Another collaborative effort is the use of field spectroscopic telescope. This telescope is also a parameter size, segmented pole mirror design, equipped with both multi-object spectroscopy and integral field spectroscopy functions. Its small capability is designed to support up to 20 spectral fibers. In China, we are building our expertise in operating LAMOS for galactic studies with 4,000 fibers at work, which is still conducting extensive scalar spectroscopy. Additionally, we are also actively participating in the DESI project as a key builder team. Our university astronomers are also eager to delve deeper into spectroscopy in their studies. Here, two significant projects in this regard are one is the 65-meter spectroscopic telescope called the MAST, which belongs to Tsinghua University, and another 4-meter telescope called the JUST, which belongs to Shanghai Zhaoping University. And both of these telescopes have secret funding and are scheduled for deployment within the next year at a newly developed site in Qinghai province, the west part of China. And so next we come to a fundamental question: what should be the top priority for national math science facilities in mainland China? Actually, we have opportunity to make proposals every 5 years. We successfully secure the funding project like most and faster respectively. Unfortunately, we faced consecutive failures to secure funding in the 12th, 13th, and 14th plans. We are now to turn our much attention to the 15th five-year plan. Just to mention a side note, in 2016, actually, a so-called China Large Object Telescope concept was chosen in the 30th five-year plan. However, we encountered challenges in the feasibility study phase, primarily due to a lack of consensus on design and a choice of construction site. So in 2019, it's a setback to the initiative. So as of now, CLOC remains on the pending list for funding. There's approximately $400 million for its realization. Then the next, let's discuss. No, I think so. Next, we come to such a final question: what should be the top priority for national next science project in China? Give you here. I think this move. Just to provide a quick view of what the CLOC looks like. Actually, one of its distinguished features is a quad mirror design. So next, let's discuss the rationale. I'm proposing to build two twin ball mirror facilities because both MSE and CLOC have converged in their conceptual development towards a 12-meter segmented ball mirror design telescope. Proposing that could transition from a general purpose facility to a dedicated spectroscopic telescope located in Chile, named the China Southern Sky Spectroscopic Deployment, SSE or SSE. This kind of consolidation would enable global spectroscopic coverage with two twin facilities, MSE and SSE. Furthermore, consider the inclusion of the WSP I mentioned earlier in this initiative to be able to further benefit global communities. I sense this was a lifetime opportunity for mainland China to take the lead in building an international scale scientific facility for a unique advantage in astronomy. However, to explore this idea further, we encourage open discussions and collaboration. I don't know how if I run out of my my time. I can stop here to take questions. There are still two slides left.
Yeah, you can go on.
Okay.
Yes, Suijian, please go.
Okay. My group becomes anyway, okay. So to explore the so-called next generation things as for initiative, we held a workshop in Beijing with some involving staff coming from both TIFR and MSC. Actually, Shiang-Yu Wang also participated in the program. And eventually, after this workshop, both sides expressed a strong willingness to pursue further collaboration. And as I mentioned earlier, we ought to run with the 15th five-year plan to commence in 2025. There's a great proposal cooperation. I stop here.
Thank you, Suijian. Now open for questions or comments. Any comments or questions for Suijian? Okay, if not, we thank Suijian again. Thank you very much. The next talk will be given by Jennifer Wiseman from NASA. The title is Hubble and the Webb, the power of the synergy between space and the ground-based platforms. Okay, let's welcome Jennifer.
Do you want me to a microphone here? Thank you. Okay, thanks very much. This talk is not going to be like a research talk. I want to give you a little bit of an overview of what we're doing with the Hubble Space Telescope in complement with other observatories like Webb. But I also want to talk to you about strategy for managing observatories and facilities that have been operating for quite a few years, how to make them scientifically powerful, and talk a little bit about science policy, science oversight, the things I've experienced. Right now I'm the senior project scientist for the Hubble Space Telescope mission. I work at the NASA Goddard Space Flight Center, and there's a nice picture of Hubble. And you'll have to guess how this picture was taken. I presented this earlier this week, but I am the grateful former PhD student of Paul Ho, and he introduced me to all kinds of observatories, so that set the stage for me to be able to learn about how different kinds of observatories work and how to work with them and for them. So I'm going to take you quickly on a little review of my own career path, because it's been a little bit unusual. So I started working with Paul at Harvard University, and he introduced me to working with the VLA in New Mexico, and set me up with a terrific project, which was innovative at the time, of doing a multi-field mosaic of the Orion Molecular Cloud, OMC1. We did 24 pointings. I mean, that's nothing now. Everybody does mosaics now, but back then it was a very difficult technical challenge, and we ended up finding that the Orion molecular cloud, one, was breaking up into these long fragmenting filaments, and stars were forming along these cores, along the filaments. So that was a really interesting project for my PhD thesis. Then I went on to become a postdoctoral fellow. I was a Jansky fellow and a Hubble fellow, and I continued to do ammonia research because Paul loves ammonia and he taught me how to use it. And so I studied protostellar cores, in particular these gas cores around very young class 0 protostars. So here's the gas core of the jet, the beautiful jet HH212, and I and my team mapped the contours there, what we did with the VLA, to find out that most of the mass was still in this large envelope and had not yet accreted onto the protostar that was driving that beautiful bipolar jet. And we studied the rotation rate and curve of that core and the very cold nature of the gas in this really young class 0 object. But I also got interested in that time in the bigger questions of science policy and how are decisions made. I mean, I like to think about the big picture of where science fits into world priorities and national priorities. And so after my postdoctoral positions, I had the chance to do something unusual, which is to become a congressional science fellow. And so I worked in Washington, D.C. This is the United States Capitol building. I worked in one of the offices at the U.S. Capitol region for the House of Representatives. They have a committee on science, so I got to work on the staff of that committee for a year and a half, which is a very different way of looking at science. You know, really understanding how science is seen from the government point of view, from the taxpayer's point of view. I helped set up congressional hearings on how our federal agencies were prioritizing science. This is a really interesting experience. And from that, I was introduced to some of the leaders in our federal science agencies in the U.S. Okay, so I learned about science policy. You know, why do we do certain kinds of science? How do we support it? From there, because I had learned about some opportunities then in federal science agencies, I was able to begin work in science oversight at NASA headquarters. And I've been with NASA now for 20 years in different roles. I'm now at the NASA Goddard Space Flight Center, where I've led a research lab in exoplanets and stellar astrophysics for several years. And then for the last 13 years, I've been the senior project scientist for Hubble. So I've learned from working with a specific federal agency how science policy and mission program management is done from the agency perspective, and more specifically in recent years overseeing the science program of the Hubble Space Telescope and how we manage and oversee that. So, which is an international mission, by the way. So this has been a very interesting circle, but part of my role now, it does allow me to foster some research. So I don't do a lot of my own research, but I foster a research group that's using ALMA, and so it's kind of like I've gone full circle here in this career path that Paul helped launch. So I'm not going to talk much about our research group, but I'll just mention that the research associate that works with me is Dr. Marta Sawillo, and she has led our team in doing ALMA studies of star-forming regions in lower metallicity environments, such as the large and small Magellanic Clouds. And she led a team discovery of very complex organic molecules in the LMC. In fact, found for the first time methylformate and dimethyl ether for the first time outside of the Milky Way and in this lower metallicity environment. So it's a very interesting detection that even in a low metallicity environment, you can already get these very complex organic molecules, and that can kind of be analogous to the early universe. How is it that you get such complex organics so early on in a lower metallicity environment. Now she's leading studies of hot cores where massive stars presumably are forming in the Magellanic Clouds and looking for some of these complex organics there. We also have a graduate student from the University of Maryland, Amanda Broadmeadow, doing some of these studies, and we're also studying YSO variability in some of these regions. Okay, so back to Hubble. I'm going to mention a little bit about the mission. There's some of the stats. So Hubble is a space-based platform, obviously. It's in low Earth orbit. It's going entirely around the world every 95 to 97 minutes, so it's going very fast, but it's got very good gyroscopes, so it can keep pointing very stably. It's been in operation since 1990, so we're 33 years into the mission now. Of course, it was put up here to get it above the clouds, to get very sharp images. This is the core of a globular cluster, Omega Centauri. And here is just an example of a beautiful massive star-forming region, ionizing surrounding leftover gas. So we've become, I don't know what I just did. I think maybe the battery just Okay. So it's because we've had servicing missions for this observatory that it's been operating all these years. We've had 5 events where we've sent astronauts back to Hubble, and that's enabled repairs and enhancements in mission life extension. And so we're still enjoying this mission even 33 years in, and Hubble does all kinds of astrophysics, everything from solar system studies to stars and exoplanets, galaxies and cosmology, and even looking at the effects of dark matter, dark energy, and black holes. And of course, this mission wouldn't operate were it not for hundreds of people on the ground who enable not only the servicing missions, but responding to technical challenges, even though we're not doing those servicing missions anymore because we don't have the space shuttle operating, but we're able to do quite a few things just from the ground, sending remote commands to address any technical glitches or computer glitches or gyroscope glitches. So I'm very impressed with the technical team on the ground. And now we have another very large space flagship observatory, the James Webb Space Telescope, that was launched in 2021. And so there's the launch from French Guiana. You can see some anxious and excited looking NASA officials watching the launch. This is a large 6.5 meter segmented mirror telescope designed to do most of its observations in the infrared. And like Hubble, it's a full observatory. It has a whole suite of science instruments, including cameras and spectrographs. It's not in the same place as Hubble. This is not to scale, but Hubble is in low Earth orbit around the Earth. Webb is 1.5 million kilometers away, beyond the moon at the L2 Lagrange point. So it's very far away. It's designed with these sun shields always facing the Earth and the sun to keep it very cold. And Webb is orbiting the sun. It's not orbiting the Earth, so it's orbiting the sun along with the Earth. And so always keeping the Earth and sun on the cool side of the sun shields. And of course we can't service Webb like we were used to with Hubble because it's so far away. But fortunately, Webb is working very, very well. So let me just show you some examples. This is one of the early release science pictures from Webb, beautiful Carina Nebula, and you can see sort of the edge of the cloud where massive stars and their radiation winds are impinging on the edge of the cloud. If you look carefully in the dusky zones of the cloud below, you see a lot of those pillar-like structures that are often carved out in these star-forming regions where lower mass stars are still forming. And for this crowd, more recently, you might be interested in this absolutely gorgeous image of HH211 taken with Webb. And you can see that inner, very, very collimated jet with a little bit of its wiggle. And then, of course, you can see some of the effects of the shock fronts on the edges. And there are people here at ASIAA who work very hard to study that core obscured protostar region in the middle. So I'll just point out a couple of things. This is Chen-Fei Li and his team have studied very carefully what's going on in the inner core and envelope of HH211. And we just heard a talk this afternoon by Suijian and team on studying the mass-to-flux ratio and the magnetic field around the core of this beautiful region. So these are examples of how space-based and ground-based facilities can complement one another in getting the full understanding of what's going on. Okay, so Webb and Hubble see different ranges of light. So there's the Hubble sees visible, infrared, and ultraviolet light. Webb sees infrared out to the mid-IR. So when you're looking at any region like the Eagle Nebula here, you can see different features. And so these help us understand things better. The visible light on the left gives you the reflected light that gives you the structure of this Eagle Nebula. The infrared from Hubble on the right gives you, it sees through the dust, you can see more stars and structure. And then Webb sees deeper into the infrared than even Hubble can see. There's the Webb image of those same pillars, side by side, Hubble visible, Webb infrared. And I saw a poster out here from Paddle et al. Looking at the magnetic field structure with JCMT along those pillars. So again, another complementary use of ground-based and space-based telescopes to get much more information. Okay, so in my last couple minutes here, I want us to think about, with Hubble as an example, but how do you keep a long-term operating mission, Hubble's been operating for quite a long time, successful? And so one of the things we've learned is to make sure that we're using the mission in complementarity, as I've just given you some examples, with other telescopes in space and on the ground. Here's an example paper of looking at a star-forming region, NGC 602, in the small Magellanic Cloud, where you have a Hubble H-alpha image showing you the stars and some of the gas, and then you have YSO candidates picked up by Herschel and Spitzer, and ALMA looking at where the CO clumps are. And from this you can determine that there's probably sequential star formation moving out in this region. So the complementarity is very powerful. We also have a long time domain here at Hubble, looking, for example, in our solar system over decades, we find some trends. So one of them, for example, is that cloud patterns on Neptune, as seen with Hubble on those top images, come and go in the same cycle as the solar cycle, as seen in the graph of the up and down there. You can see the solar UV radiation rising and falling in 11-year periods, and the clouds on Neptune responding to that with just a tiny bit of a time lag. We wouldn't know that if we didn't have a long time series. Okay, so I'm going to quickly point out that we are also using Hubble's ultraviolet capabilities as best as we can. So we have, these are just some examples of the large observatories available in this decade, a few of them, and their wavelength coverage. And so you see most of them cover visible or near-infrared light. Webb goes out into the mid-IR, but Hubble's really the only flagship observatory until the 2040s that goes into the ultraviolet. So we're trying to make the best use of that. This is our decadal survey recommendations for the future, and you see the next IR optical UV flagship doesn't get started until the 2040s. So we're making as best use of that as we can right now with Hubble to try to get as much data in the archive as possible. Okay, so a couple other quick things that we're doing with Hubble to make sure that we keep it as successful as possible is the archive, making sure that the data is put in a very accessible archive. And so these are our publications. They continue to grow, but nearly half of the publications are coming from data pulled out of the archive. This is great news. It means Hubble is getting good use of its data and will for many years to come. We're also making innovations in how we select science. So we started something called dual anonymous peer review, and now many other missions have adopted this as well. It's designed to help remove any unconscious bias in the selection of science proposals. And what that's done, as you can see on the right, is that it has made a huge difference in the percentage of proposals that are getting accepted to use Hubble that are led by first-time principal investigators. So these are teams that really haven't had a chance to use Hubble before, or they come from smaller institutions that don't have that heritage. I don't know what
Sorry.
but it must be the chair telling me to finish it. So anyway, innovations are important, and we're looking also to the future when we'll have the Roman Space Telescope. These are the fields of view of Webb and Hubble compared to Roman. Roman's going to be a large survey telescope. So how do you keep a long-term astronomy mission facility successful? Well, some of the things I mentioned is that we try to keep working with our stakeholders. We try to align our mission priorities with the changing landscape of national and international science priorities. We have a good technical ground support team. We work with other missions to develop complementary science goals and capabilities. We try to develop innovative ways of selecting science and building inclusion, better archive, energizing public outreach, and designing a facility to be upgraded if possible. So, the takeaway messages for us today are that successful science, this is why I brought in my own career path, we need people with diverse skills and roles, including people who are experts in research, of course, but also in science policy, public engagement, communicating, technical skills, an eye for interdisciplinary possibilities like astrobiology, for example, and even commercial participation. So we need to bring in and encourage diversities of skills and career paths. Astronomy success in the future will flourish with complementary and innovative uses of different telescopes and probes. And how do you keep older missions and facilities at the forefront of science? Where you dynamically keep realigning your mission science priorities and your policies and participation with changing international science priorities in the landscape of facilities and missions. So I believe astronomy will continue to inspire, and I will just say that Hubble science is continuing. We use Hubble images in this school for the blind, where people can feel the images with different textures for different astronomical features and really get excited about what they're discovering. The top right is a window at a church near Johnson Space Center, and all the stained glass windows are modeled after Hubble images to inspire people. And even U-Haul moving vans are inspired by Hubble astronomy. So thank you, Paul, for inspiring my career. And I will leave with these websites for Hubble images. But last night, Paul was kind of jealous when I was giving some Hubble bookmarks to a child at a restaurant, so I have some for you, Paul. Including the little backpack that you'll enjoy, and some Hubble images as well. And the surprise is that I have these images and bookmarks for all of you too, and I'll put them back on the outside table. All right, thanks very much.
Okay, thanks, Jennifer. Due to the time limitation, we have a quick comment or question. Okay.
Hello. I have actually I had a quickly calculation of the budget in China spending on astronomy project. The answer is about $1 per person. And also in the Astro 2020, it lists the astronomy budget in the past years in US, and it's about $1 per person for US. And for Astro 2020 is very ambitious. I think it requires 3 or 4 times more budget in the next decades, a few decades. So from the government view, do you think it is possible to increase such large amount of budget on astronomy?
I don't know. So that's a good question. Like, can you keep increasing the amount of money going to astronomy? Probably not. But the other way to handle this is to become more efficient with your older missions so that you're not necessarily increasing the total budget. But I can tell you we're under a lot of pressure right now to try to figure out how to balance this. But people are very supportive of astronomy. So I think if they feel like they're getting something out of it, that's why we make sure all of our images are made public and easy to access, then they're more supportive and enthusiastic about supporting it. So thank you.
Okay. Let's thank Jennifer again. Jennifer is some kind of our godfather. So I let her among times for this talk. We are over. So I will still stand up maybe 2 minutes left. So please finish the talk. Okay. Otherwise we will be delayed a lot. Oh, the next talk given by the Dharam Lal from the National Center for Radio Astronomy. The title is superMIGHTEE projects. Okay, let's welcome the Dharam.
Thank you for having me here. 2 days back I shared I was shifting from here to Max Planck Paul, and Paul asked me, he supported me all through, but when I was moving he asked me, what are you going to do there? And I was hired to do array configuration studies for Square Kilometre Array, and I said I will also probably to continue to do my projects using GMRT. Paul's answer was, SK is so far away, forget about it. GMRT is a great instrument, build something big project using GMRT. So Paul, this project is along those lines, and I'll try to convince you that. This is on behalf of core team. I'm Dharam and Raj Taylor from South Africa. We are PIs of this project. Other person is Shiang-Yu and my colleague from NCRA, Ishwar Chandra. So I'll be talking about this MIGHTEE fields, which you can take it up to GMRT side. So what you see over here is a MIRCAT instrument, and down is the GMRT instrument, and I'll try to convince you that two observatories, when brought together, what best science work can do with it. So when MIGHTEE project came up, until SK, it will get integrated as an SK project, and until that happens, MIGHTEE has some large survey projects, and these are listed over here. What I'm going to pick up is the MIGHTEE project, which is MIRCAT International Gigahertz Tiered Extragalactic Exploration is the full form. Deep continuum imaging of the early universe. And what it focuses on these four fields: XMM-LSS, Chandra Deep Field South, Alliance South 1, and Cosmos. These together comprises 20 square degrees which have deepest image. These were chosen because there is huge amount of optical, infrared, auxiliary data, including X-ray, available for them. And the MIGHTEE project, the PIs for these two gentlemen. So essentially, these were the fields for various XM, LSS, and others. And 2,000 hours were awarded on MIRCAT. So what we thought is, why not supplement GMRT data to this? And why we wanted to do is the following. Around 2017, we had just accomplished the upgrade of GMRT. And this slide is a primer on upgrade of GMRT. What you y-axis you see is occupancy, the bandwidth, and the operating frequency ratio of this as a function of various bands of GMRT. Before the upgrade, we only had 20% or few percent of occupancy in this. And once we upgraded it, this is what happened over there. We were close to 70% at the lowest end of the frequency and close to 30% at the highest end of the frequency. This yellow patch over here is what MIRCAT is doing for this frequency band. And what you see over here is this is largely due to change of feeds to broadband feeds and various backend upgrades. So we also looked at why GMRT should be supplemented with a MIRCAT. So this is a MIRCAT array configuration. You have dense codes arcs going out to 8 kilometers, and GMRT also has similar dense codes. Half the antenna are in center square. arms going out to 25 kilometers. So at L band over here and band 3 or band 4 over here, you get nearly identical angular resolution. In addition, if you look at the UV coverage, those are also very identical. So we are sampling identical spatial structures as well. This plot is showing RMS sensitivity as a function of frequency for various instruments and precursor instruments. So the GMRT blue point for the legacy GMRT sensitivity for 9-hour observation, and after the upgrade they became a magenta point. So just focus on UGMRT band 3, band 4, and this is a MACAT point over here. So we essentially have identical sensitivity in a 9-hour observation for various fields. So we essentially used combined data sensitivity. This gives us micro-Jansky level sensitivity all the way from 250 MHz to 2.7 GHz if we combine these two observatories simultaneously. Well-matched resolution, you can then perform spectral analysis from 0.25 to highest frequency of MACAT and within MACAT band also and UGMRT bands. So what we are giving to the community is the following: ultra broadband spectral data as well as polarimetry data to measure Faraday complexities. If you want to do Faraday measurement only with MACAT data, you will have some fantastic result. But if you just add GMRT as well, it improves by 3 times at least. I'll come to this a bit later. So this essentially samples improper frequency curve range just to understand complex depolarization or repolarization in various sources. Of course, we give you a spectral structure across the whole band, so you can perform H1 science by stacking at high redshift as well. This plot is little modified. So what it is showing is sensitivity limit and coverage area, and these are various existing surveys. This is a limiting survey for most of the instruments. Square Kilometre Array, when it comes, this is going to fill up this parameter space over here. And currently, the superMIGHTEE project will fill up this parameter space. It will be lower in sensitivity, though smaller coverage area. So we started with this project in mind, and as soon as the upgrade of GMRT was ready, we started with a pilot project. So we essentially wrote proposal, time allocation committee gave us some time, not all of it, and this was in late 2019. We performed observation at band 3, band 4. So what you see is red part is MACAT pointings, green is band 3 and blue is band 4. And this essentially gave us the first images which we are talking. At band 4 we had micro-Jansky level sensitivity, and at band 3 we had a factor of 2 or 3 more. This formed the PSC product of Hubble occurrence. So what you see over here is band 3 and band 4 images. We had some 2,500 odd sources. We looked at the distribution in terms of spectral index at these two bands. We also looked at how the number of sources is distributed in radio loud and radio quiet. The bottom line of this thesis was, in the nearby universe, the faint source population is largely dominated by star-forming galaxies. So then we opened up the whole project to larger community, and whosoever wanted to pick up their own science drivers could have raised, and they took up various projects over there. Of course, the core team continued to work on various issues which we were facing. I'll come to those, high dynamic range imaging, etc. So I presented, this was in late 2019. Today, we have approximately 1,000 hours of observing time for these 3 fields. This cannot be covered by GMRT. At various bands, this number is not double. We have got another 16 hours of observation in the current cycle, and this is the MACAT which is complete. So now that we have this, so from here onwards I will be talking about early results from the superMIGHTEE project. So what we have done is, we have band 3, band 4 and MACAT L-band data. We can essentially determine spectral index at low end of the frequency and at high end of the frequency, and just make a scatter plot. color code by brighter sources to fainter sources, and sun and wind are in between these, and ask the question, how are they distributed? So this is what it is shown over here, and you can further divide it into 4 different quadrants. You have conventional spectra, peak spectra, inverted spectra, and so on and so forth. I mentioned about issues which we are facing, the high dynamic range. If you look at this closely, this is a point source which is got diffuse smudged because of ionospheric effects. And this is lastly called direction gain errors. Don't get scared with this equation. This is just astronomical techniques advanced course, one primer on that in radio interferometry. This is your sky brightness distribution, and this is your observed visibility. Gain of the dual interferometer, weights of each of these things. What you see, this function and this function. First one is direction dependent errors due to ionosphere calibration. Second one is we have GMRT 30 dishes. Not all 30 are identical in the sense that they have flexure, there are issues over there. So that creates the antenna primary beam issues. And then of course the 30 antennas are not lying on the same plane. You have essentially the blue color issues. This whole equation you can modify and write it over here. And so essentially you have weights, observe visibility and true visibility. In this, the AIGS is nothing but the aperture illumination pattern of antenna. If I have this information, then I can correct those direction dependent errors completely. And that is what we are trying to do. It's essentially a function of antenna frequency, position angle, and polarization. So this recipe, we have it, we are not there. I want to just display using this thing that this is for the VLA antenna, main lobe, first side lobe, second, third, and if you just invert Fourier transform, you essentially get the aperture illumination pattern. This is also done for the MIGHTEE antennas. For the GMRT antennas, we are not there. If you look at it more closely, this is the main lobe and this is the first light lobe. We need to go to third side lobe to get the aperture illumination pattern, to get the full polarization products. Having said this, we do have polarization results for some of the early results. This is one example from the XLM analysis. This is FR2 radio galaxy, giant radio galaxy. This whole structure is 1.1 megaparsec in size. What you see is radio contours are polarization intensity radio contours. Vectors you see are position angle of the polarization angle. This is K-cut L-band image, and this is UGMRT band 4 image. The change in polarization angle and polarization intensity is due to Faraday rotation measurement. Sorry. Next, I want to introduce what we are planning next. So we essentially, I want to show you what polarimetry we are aiming for. So just focus on this little plot. This is Q and Stokes Q and U as a function of lambda square. If you would have had only MIGHTEE data, this is what you will be sampling. But if you supplement the UGMRT data, this is whole band is what you are sampling, and this is crucial. You can do the same thing for the polarization intensity as a function of lambda square. This is what you get. And this is very crucial for the factor of 3.2 which I mentioned you earlier. And if you do this, I'll show you polarization result for one source in the field of view. So this is the polarized intensity as a function of frequency. This is Stokes Q and Stokes U as a function of frequency. The background Stokes Q and U, just to understand how much is the background noise. Now I can plot the polarization fraction P, Q, U, and V, which is over here. And if I do the rotation as a synthesis, I clearly see a peak at 14.2 radians per meter square for this source. I can then perform this exercise for all sources in the field of view. This is for the cosmos. Apart from 4 core members, people who are witnessing this result are present in this room. So what I am showing you is sources which are negative RM are in red, sources which are positive RM are in green. Size of the circle reflects the amount of relative RM. And that is what is for the MIGHTEE L-band data. For the same field, this is the GMRT band 4 data. We still are looking at all caveats around this thing. for example, amount of rotation measure contribution due to ionosphere, etc. And this is the T. Since chair has stood up, I'll just take half a minute more. So now at this stage we asked for more scientific drivers. So there are people, there are student PhD projects, people who want to move down from student PhD project to postdoctoral stage, PIs who are faculty position want to take it up for the student project, and of course some of us are involved in the technical aspects still. So I just presented a synergistic project using UGMRT and MIGHTEE. If you bring two observatories from different places together and what can be done. For SK, if you want to compare, this will be SK mid in South Africa and SK low in Australia. That is what we will be doing it over there. An ultra broadband deep full scope survey. We provide standard continuum spectral information, and along with that, a polarization information for every source in the field of view. And on behalf of superMIGHTEE team, I thank you.
Now open to the question or comments.
I just missed adding that if someone wants to have their own science drivers, you can raise hand, come and talk to us. We are open to making this data available to them.
Okay, so there's no question. Let's get the round again. So next speaker is Kaiyang Lin from ASIAA. The topic is the Earth development status. Okay, let's welcome the Kaiyang.
Hello, thank you. So my name is Kaiyang Lin from ASIAA. So I started my career as first as a PhD student in the AMIBA project, working with Paul. And then I moved on to build more telescope, one project after another. And this is the latest one that I'm involved. This is the first project, the Boston Universe Radio Survey Telescope in Taiwan. And PI is Wei, and this team currently involves ASIAA, NTU, Tsinghua University, Zhongxing University, and Zhanghua University of Education. Okay. And as the name suggests, the telescope is really about finding FRBs. And FRBs are millisecond flashes in radio that originate from extragalactic sources, but the physical mechanism is still unknown. And only a small fraction of these FRBs are known to repeat. That means most of them either don't repeat or repeat at a much lower signal level, or they repeat but we miss them during the observation. So the key challenges here is that the FRBs can happen anywhere, anytime. And to address this challenge, our response is that let's build a telescope with a large field of view and enough sensitivity by putting a large array of dipole antennas. But the key to understand the physical mechanism is through multi-wavelength follow-up observations. And to do that, we need to know this precise location of the FRB and which host galaxy it came from, and better if we can know the local environment of that FRB event. So to answer that, we need to localize these events using single bursts, because most of them don't even repeat. So our answer is that let's build a few more radio stations and do VOVI with them. Observation. So this is the concept of burst. Details of this white paper is published in PSP last year by Suijian Li. And basically we'll build a antenna array with a field of view of about
10,000 square degree. And we would like to be able to localize the sources to 1 arcsecond resolution, and probably better, depends on how far away we can put those outrigger stations. And this figure shows the projected sensitivity and field of view diagram. So we plan to build the BURST project in 2 phases. The first phase with 256 antennas, and maybe with 2,000 antennas later. So with 256 antennas, we'll be reaching 1 FRB in a couple of days. And with 2,000 antennas, we expect to see several FRBs, 10 FRB each day. And this is the current sites that we've been investigating and developing. And the main site is in the Fushan Botanical Garden in Yilan. And right now, this site, we built this platform to host the 256 antennas. And we have deployed 64 antennas to the site already. And there is a second, first outrigger station in Nantou. And here we also already deployed 16 antennas for some initial testing. And we have a testing site in Cape Fugui, close to Taipei. And we have 16 antennas there. And in Green Island, we also secured the site and is in the process of developing the site for construction later this year. And where the longest baseline we have been investigating in Taiwan is in the Dongsha Island. There we have also still in the process of negotiating for outrigger station. And that way we can have 600 kilometer baselines with the main array. And yeah, the shortest baseline here is about 140 kilometers. And for the Cape Fugui station, because the size is small, relative constraint, so we're probably not really developed into a full outrigger station, but for a good testing site. And on this figure, I'm also showing a lot of dash line to other places, like in Thailand, India, or to Japan, Sorara Island. And these are potential collaborators that we've been talking, and also sending testing equipment for surveys. So potentially we'll be able to put our outriggers with thousands of kilometers baselines to make the angular resolution 10 times better. And our design, we didn't use specially designed FPGA backend system. Instead, we are using commercially available development board from Xilinx for the RFSoC. It has 16 input channel, so it can digitize 16 antennas at a time. But what's important is that with these 16 inputs, once it's done being transformed into spectrum, FPGA can host one matrix multiplication component. The purpose of this matrix multiplication is twofold. One is to combine these 16 antennas into beams on the sky. So instead of each antenna, we now have 16 beams in say one dimension. And another function of this matrix is to suppress the RFI, so we can characterize the antenna voltages and calculate the suppression, and we can put that into the same matrix for one operation to both do beamforming and RFI suppression with this tool. And we need to do this before we truncate the data into lower bandwidth for transmission to the computer. And this is the testing result from our Fushan setup. So on the left-hand side, I'm showing the spectrum from Fushan. This is the FPGA is processing actually the entire 800 megahertz bandwidth. And we're only sending out the 400 megahertz for processing right now. And the lower 400 megahertz, we see a lot of oscillation. That's because of the antenna design. There's a strong reflection. But on the higher 400 megahertz, we see features like TV signal and 4G mobile signal. But other than those, the spectrum is actually pretty clean. And on the right-hand side, I'm showing the example of the fringe observed from the sun. And this is the phase as a function of frequency and time. So we see a clear fringe, and indeed most of the band is clean, except for the TV and 4G contaminations. Okay. And we also use these some fringe to characterize our system, including the antenna front end and the side environments. And we got the system temperature around 120 Kelvin. And the antenna correction was applied, which was separately measured in the anechoic chamber. Okay, and I'm also showing here the beamform result from our RFSOC's backend pipeline. So we transform the antenna voltage into 16 beams on the sky. So these are 16 beams. And the first beam, we can use a sum to map these beams. So some entered this beam first, and gradually the beams are on the western and western direction, so the beam enters this beam last. And these curved structures are the silo from our beamform process. But those are useful too. So we can search for FRBs in this main beam, but we can also search for FRBs using the silos. So those will be useful in our future operation. Now, for VLBI, that's one of the key challenges. How do we keep timing between our stations? And we are not proposing to use very expensive maser systems. Here we're trying to utilize the rapid development in the GPS timing industry. So our plan is to use this RTK, real-time kinematic measurement, which is also GNSS technology. They will talk with each other over internet, and even when the two sides are physically separated by, say, 100 kilometers. And we'll try to solve the time difference between these reference signal, which block to the RFSOC system at each site independently. So this is an important part about the VLBI capability of our project. So initially, we like to see how significant these clocks vary. We can verify their performance. So first, we just for each RFSOC, we connect them to a different clock, but now they are at the same site. And we can use an external time interval counter to measure the time difference between these two clocks. And we can also use the fringe of the sun to determine the difference of the clock if we subtract the geometric delay out. And this is the testing result. For 3 hours, we can measure the variation from the time interval counter and also from the sun fringe measurements. And their difference is very small. But remember that the RFSOC operate at 400 megahertz, and the reference signal is at 10 megahertz. So at least using these measurements, we verify that if we can constrain the timing error on the reference signal, and we can transfer that error to the FPGA timing error. And the agreement is better than 0.2 nanosecond. And if we look at the shorter time scale, that within here example within 8 seconds, we can see that the clock has been very stable within this short period of time. And we further start to test the RTK device using a similar setup with a TI time counter, calculating the time difference between two clock sources, and we can try to measure the time reference using the RTK technology. And the first test setup was in this building. So this is a zero spacing testing, but it shows that again within 3 hours we can see the exact match between these two measurements methods. At this moment, the RMS scatter is still about 1 nanosecond, which is barely useful for our VOPI, which our goal is to reach 0.1 nanosecond. But right now we still have some problem because in our institute we have only half the sky, and there's a very significant reflection multipath problem. So for the next step, we'll move to open sky, and there are also other improvements we can make with the solution in this two devices. So hopefully we can reach 0.3 nanosecond without much trouble. And then we'll move on to testing this capability at more remote site, longer separation. Okay, so that's the status of our development now. So we have a main array with 64 antennas and still deploying more, and more outrigger stations being developed. We've successfully used a sound to characterize our system, beamforming, and do various testing successfully. And now the focus is on securing the timing capability of the VOPI part. And one more thing to mention is that using the GNSS measurement has one more advantage, that we have a continuous estimate of the total electron content toward many GNSS satellites at each site, meaning that we might be able to use this kind of total electron content to model the atmospheric delays of the pulses from FRB or from pulsar. And that's still challenging, but that's one potential advantage of this method. So stay tuned. And if you're interested, come find me. You can talk. Thank you.
Thank you, Dharam. So now, any questions or comments on Haiyang? Just a simple question. I'm doing the implementation. In the phase 2, you have the 2,000 antennas. Is a big array, or do you need to send some in outrigger?
So for this, to increase sensitivity in the detection process, it has to be a single array. So we do need to find a large area for this large array.
Okay.
And outrigger doesn't need that much sensitivity on a cross correlation for localization only. But if we have larger main array, we also want to increase the size of the outrigger as well to also increase the sensitivity at the same time.
Okay. Yeah. Thank you. Okay, there's a question. Yeah.
How big a problem is the ionosphere at 400 megahertz? How much total delay could you have, and realistic situation?
That remains to be seen actually, because what I heard from the expert is that whether we can reliably do the timing to remove this atmospheric delay from the timing measurement is a challenge. So maybe we have to limit our separation between timing stations. Maybe we need to put intermediate timing stations. And whether we can use that total electron content estimate to correct for the FRB delays, that's another challenge. So whether our GNSS sample is continuous, it means that satellite will track, and we can have a kind of database. But how well that can work still is something we have to try.
Okay, I think that we have to move on. Let's send Taiyan again. So the last talk is given by Shiang-Yu Wang from ASIAA. The title is Development of the OIR Instrumentation Capacity in ASIAA. Okay, let's welcome Shiang-Yu.
Okay. Yeah, so I'm here to talk about sort of give you us a history of how we do the astrophysics instrumentation in our institute, and which essentially has a lot to do with more. He's actually the one in fact to push all of this. And actually the first thing he did is actually hire me. I remember when I visited the institute for the first time. Before I joined the institute, of course, I saw the director, which was Fred Long at that time. So I talked to Fred about 30 minutes, and then he said, "Oh, you should see this guy." And he brought me to another office, and then he said, "Oh, please stop." And I talked to Paul for maybe an hour, longer than Fred, and then he said, "Oh, welcome, join us." So that's it. This is actually what happened when I was hired. So I still design. This is what Paul usually used to show when he was a director, sort of showing the roadmap of Asian projects. And actually, the bottom part is all the OIR activities, and most of it is actually pushed during Paul's leadership. So I'll just quickly walk through this, and then hopefully you can understand how important it is with Paul's help. So the first project that we initiated in optical infrared is joining this wide field infrared camera for Canada French Highway Tesla. So at that time, I'm just really a fresh guy in instrumentation. So I was sent to Hawaii and work with people there. So we basically work on electronics and also related to the detector development. This is a sort of first experience. But after that, we actually stopped a little bit. So we have actually tried. We have this training process with CMHT, and then at that time, Typhoon was pushing for the Taos 1 project, and then we put it in operation phase in 2005. And then at that time, we started to think about what to do. There was some cooperation. We formed some team with Sophia Iris team, but it didn't really get through. It got canceled in the meeting in roughly 1 year. So it sort of got stuck during 2005 and 2008 during this period. And then during that period, that was Paul that's initiated 2 major projects to get it going. The first one is a hybrid springcam with Subaru telescope, and he also helped us to push for the second generation of the Taos survey. So that leads to these 2 important events. The first one is we signed a MOU with NAOC in 2006, and then this is the groundbreaking ceremony for the Taos 2 sites in 2013. Yeah, so you can see Paul was there for both of them. I was not. So How important was. Yeah, so actually, you see, in the beginning we have this two project that sort of ends in 2005, and then we start to have Hybrid Sinica, and then continue with CRT for the Spiru project, and then second project for the Subu PMS Tiles 2, and then some space missions, including the ERG and Spica, and then we move on to the EOT instrumentation formatics, which happened in 2018 when Paul was no longer the director, but this project was also initiated by Paul. I remember I visited Mass Planck Institute with Paul and talking to Thomas Henning and other people to see if we had any chance to join the EOT instrument. And luckily we were able to join one of them. So I in the following slide, I'll just show you what we did. To be very quick, it's for Hypersinica is a wide field optical camera. I think up to now it's still one of the most powerful camera in the world. It's a very big structure, 3 tons, and also 3 meters in size. It's a 9 megapixel camera, covers 1.53 field view. It's a very superb image quality. And during this project, we start to accumulate our capabilities in high precision machining, highly reliable robust system. So we did is we built this filter exchange system that can be repeatable in positioning in 10 micron. And we also involved in the highly integrated CCD real system. And then, as I mentioned, Tao is another important project that Paul initiated. He actually threatened our academia president that if you don't give us the money, I'll just quit. So that's why we got the money for this project. And this project is eventually happening almost now. We're going to start our survey pretty soon. The goal is to follow 10,000 stars simultaneously with 20 Hertz sampling, so that we can catch a rotation event in which has a duration around 200 milliseconds. So we have just deployed 3 telescopes and also with 3 mosaic CMOS camera. This is one of the testing images that we got recently. So right now we're getting to a point to do optical confirmation and then integrate the whole system and make sure the robotic control system works well. So in this project, we also learn about for the telescope side relevant and then the camera system, sensor technology, and also the focal plane technology. And for the Subaru project, we continue our efforts and cooperate with them to build a multi-fiber spectrograph with them. So this is a huge project with partners in France, in US, in Brazil, Japan, and Taiwan. So it has 2,400 fibers with steerable positors, which feed the satellite to a 4-bit spectrograph covering from 0.38 to 1.25 micron range. So in this project, we build we call it a charge camera, which can identify the fiber position so that we can confirm, we can perform the closed-loop control of all the fiber movement so that I can arrive to the stellar object within the 10 micron area. So this has been delivered to the telescope, and now our commissioning effort is ongoing. And then this is the EOT instrument that I mentioned. Paul helped us to get to agreement to join. So it's a mid-infrared imager and spectrograph, basically covering from 3 to 19 micron. It's a huge instrument with a size of roughly 3 meter by 3 meter by 3 meter. It has imaging capability together with a chronograph with very high image contrast, and also it has a high resolution spectrograph and integral field unit. So in this project, we work on the filter wheels as we work smoothly in the cryogenic temperature, and also we build in electronics to control the chopper in the infrared. And we also did a lot to design the support equipment for the final system integration and test. So, and then during this process, somehow we are also involved in a space mission. This is one of the missions we collaborate with Japan for magnetosphere studies. So together we built a low energy electron probe, which has been operating in space for like 7 years. It's been working pretty well. And we were also involved in Sinica mission to develop the calibration source, but unfortunately this one didn't go through. It was terminated due to the lack of budget. So through all this project, we actually has moved forward a lot, and I show this slides again just to revise a bit of what happened. So instead of going to the space, we should move on for the ground-based optical facility more, and then we're doing the EOT, and now negotiating with GMT for the partnership. So this is a quick look backwards of what we did and actually what Bob did for us. So thank you, Paul, for all the efforts, and without Paul, I don't think any of this can happen. Thank you.
Thank you, Danny. Now open for questions or comments.
With regard to the TAOS 2 project, it would certainly seem like the processing is a very formidable problem, and I wondered how that is looking in terms of the computation.
So it's a lot of data coming in, but the good thing is that we do not read out the whole focal plane. We only read out the boxes surrounding the target stars. So these reduce a lot of the data volume, and then we, based on the first generation of TAOS, we already have the photometry pipeline and then the event detecting pipeline very solid ready. Yeah. So of course, right now we are more focused on the event simulation, so that we can fix the possible events with the real parameters.
Any other question? Okay. John?
That was really nice. Earlier today we heard from Jennifer about the lack of the UV in the near future in space, but with the Spica demise, we're really suffering in the far infrared. Is there any talk in Taiwan of thinking about, let's say, the US probes or getting involved in any of those missions?
Yeah, so I had continued some regular meetings with our colleagues in Europe and Japan regarding the US probe. But somehow we didn't proceed forward. I know that for the US probe, Netherlands, France, and also Japan, they are also involved. But internally, I didn't hear enough push from us, so I didn't really push strongly on our side. But there are still small far infrared or mid-infrared missions in Japan that we are having close contact with, so that's one of the possible ways if we want to join.
Okay, we are run out of time, so I thank Shiang-Yu Wang, and thank you all the speakers and sessions for
then the NAOC has some